Okay, so let's see how uncountable numbers are useful in real math with real applications, okay? Let's see what their cache value actually is, alright? So let's look over two applications, let's talk about uncountable numbers as such, and then we'll figure out how that actually works in those examples, alright? Okay, so let's first deal with a problem from harmonic analysis or signal analysis. Alright, so one thing that happens a lot is I send a message to somebody, but I really only want to send certain frequencies in that message. Like, if I call you up on the telephone, or if you listen to a video of mine, then you don't hear like my full voice, you just hear a certain set of frequencies in that voice, alright? So my voice, let's just say, is made up of, like one sort of normal frequency here, sine 2t, something like that. Then there's another like higher frequency, which is very quiet, but there's a quiet frequency in my voice, which is like 1/10. Say 1/10 sine of 8t, right? Higher frequency, more bumps, but it's lower amplitude, so it's quieter. And let's add another part of it was a big but very low frequency like this, okay? And that's like 5 sine t over 4, okay? Low frequency. Alright, so you add up all those, and those roughly approximate the sound of my voice represented by f of t. Alright? So that's good. Now, one thing here is that this is maybe a good first approximation, but you might be interested in maybe adding on more signs, right? Many more signs, in order to make it a better approximation of my voice. So you'd be curious of how to do this in general. Like, what does it mean to keep adding on more and more of these waves to approximate some function like my voice, which might be arbitrarily bizarre like that. Okay? Alright, so we see that adding up signs and adding a whole ton of them is useful. So let's do a particular situation. Let's say you're given, some combination of these guys. Something like sine. I'm going to do cosine just to make my life less agonizing. Cosine pi t. I'm going to put the pi in there just so that it's a little more straightforward for me. Cosine 2 pi t plus, let's say, 1/2 cosine 4 pi t, etc. Okay? More and more higher frequencies thrown onto there. And you get this series of sine functions here, or cosine functions. And you realize, okay, I got a great idea. I figured out a way of rewriting this. I'm going to rewrite these guys as cosine 2 pi t plus cosine to the 10th of a slightly higher frequency one, and then cosine, let's say 100 on 8 pi t, so on and so forth, okay? Okay, so we're doing that. Now, what does this look like? What do these guys look like? Well, the first guy is like perfectly normal, like here's 0, here's 1. Actually, let me just modify this a little bit, guys. Let's make this into 20 pi t, and let's make this one into 200 pi t. Okay, so 10 times. Now, what does this guy look like? Well, this is just regular cosine of pi t, right? Looks like, let's make that squared, just to make my life less hellish. Looks like that. Right? Never negative because it's squared, right? So, okay, that's all well and good. Actually, it's a little bit different than that. It looks like, actually there's two frequencies in here, like that. Okay, so that's reasonable. That's what the square does, makes it completely positive. Look at this guy here. Alright, well, I'll deal with that 20 in a minute. Let's just say I took this to the 10th power instead of the second. What would this look like? And then I'll sort of add in maybe extra frequencies there. Well, that would look like something like this, where right here at 0.5, I would take the 10th power of that, right? And 0.5 to the 10th power is really small. And, well, here's 0, and 10th to the power of that is really small. And here's like 0.9, and, 0.9 to the 10th, that's going to be a little bigger. And then 1, all the way up here, that's going to be just 1. Right? So, basically, it's flat most of the time, and a sudden jolt up, and it's flat most of the time, sudden jolt up. Okay? And it's very high frequency, right? It's got 10 times higher frequency than that, so we have a whole bunch of these spikes. Okay? Whole bunch of really skinny spikes. Alright, now, this isn't quite right for the numbers here that I put up here, but let's just say hypothetically that each of these spikes right here is 1/10, is 1/100th as big as that spike right there. So the area under this spike right here is 1/100th of the area of this spike here, and there's 10 times more of them, okay? So if this, hypothetically, had an area of 3, I'm just going to make up a number. This right here has 10 times as many spikes, but they're all 1/100th of the value. Okay? And same thing with this here. It's going to be, let's say, 100 times each of those spikes. There's going to be, in this case, 100 times as many spikes. But each of those spikes, instead of being 1/100th as big, they're 1/10,000th as big. Okay? So this gets you 0.03 for the next guy, who is like just like a whole bunch of spikes like that. Alright, so now you're looking at this and you're feeling like, okay, this is a little weird here, but alright. This guy, if I add up all these guys here, it's like, oh, 3 plus 0.3 plus 0.03 plus 0.003, so on and so forth. This seems like it's, oh, I'm adding on smaller and smaller areas here. The extra function in the next term and the next term after that is getting more and more minuscule, more and more marginal, until maybe the point where I can just ignore it. But the thing is I'm very curious to find, well, what function is this actually approximating? What is it tending towards? And there's a problem when I try to figure out what the actual function that these guys are approximating. Okay? And the problem is basically this. If let's just say I was interested at, let's just say this is approximating the function f. I ask, alright, well, according to this, what is f at like let's say 0. Let's say 0, okay? Well, okay, I plug it into these guys, and what do I get? Well, I plug into 0 there, and I get 1. I plug t equals 0 into there, and this is 0, and I also get 1. I plug 0 into there, and I get 0, and I get 1 here, too. Right? It's always 1 right there. So it actually is sort of like, oh, well, this is going to be like infinite right here. If I evaluate this at 0. That's a problem. That's just sort of an artifact of the way I'm adding this up, but that's iffy there. It feels like this is adding up to a real function, but okay, screw it up at 0. Let's try another one. Let's try another one, guys. Let's try 0.128. That should work. That'll definitely work, right? Well, let's see. 0.128. Okay. It's like right here. And, oh, yeah, it's out. It's not there. Actually, let me do a little differently here, guys. Let's just do 0.1. I do 0.1. So 0.1's like right here. And okay, 0. 0. I'm very proud of myself. It's 0. I then try another guy. All right, so I put 0.1 in here, and it's roughly 0, or is this very small value. And it's not 0, it's very small value. I then plug into here, 0.1, and it's like, this is 1 now. I plug in 0.1 into here, and again, it'll be 1 over here. Okay, so again, this is infinite, right? Alright, that's something that's really screwed up. Let's do like 3, 1, 4, 1, 5. This is actually just a decimal, not pi, okay? And I do this, okay? And I look at these guys, and okay, it's giving me a number, and a smaller number, and an even smaller number after that. But by the time I get to like the 6th one of these guys, then it's going to be on one of those spikes again, right? Because all of these guys right here, their spikes are at the decimal values. So here it's like, it's at 0, and 0.5, and 1. Here it's at like 0, and 0.1, and 0.2, and 0.3, and 0.4, all the way up to 1. Everything like this. Then I have this guy who is everywhere, like 0.xx, you know, anything like 3, 4. So on and so forth as I get higher and higher. So this guy again will be an infinite, alright? So this is a problem here. This is a really serious problem. This, which seems like a natural kind of sum to make, right? It's a very natural sum to make because these functions here, these waves over 0 to 1, have a smaller and smaller area. It should make sense that if I add up functions which have a smaller and smaller area, 3, 0.3, 0.03, underneath them, that they'll add up to some real function. But as far as I can see, any value that's like a finite decimal expansion, right? That will be infinite. Something's gone wrong. This is really complicated. Now, what if I put in a function like f of pi? Okay, not 3.1415, pi. Well, you could actually show here that this really does tend to some number. I'm not sure what that number is. Let's say like 4.1. You could do another number like this. Let's do 1 over pi, because we're going to 0 to 1. Let's say 1 over the square root of 2. This also will tend to some value like 3.28 or something, okay? If you put in irrational numbers here, then this will actually converge to something. This sum will actually mean something. But you put in these decimal numbers like 0.1, 0.31415, so on, it turns into infinite. So we have the situation of, I want this function to add up to this sum of functions to add up to some real function. It should. Its areas add up that way. But I evaluate at an infinite number of points here, all sorts of points. I mean, these are good, useful points right here. And it gives me infinite values. So what the hell? What the hell? This is a big problem. I don't know how to handle this. Basically, I'm in the situation where this f, according to this, is like, well, you know, f on the rational numbers, which we represent the set of all, oh, not the rational numbers, on decimal, I guess, let's call it finite decimal expansions, okay, FDEs, things that basically are just like a handful of numbers like this, alright, and basically there's never a dot there. This will always equal infinite, will always never converge, okay? But on everything else, it does converge. Okay, what the hell? What the hell? This is a problem. This is a major problem. Okay. So, what do we do here? And by the way, guys, I could have made this even screwier, okay? I could have made it so that this right here, instead of being 2 and then 20 and 2, I could have made it such that this was just 3 and then 4 and then 5, and then it would have had been screwed up not just in every of these finite decimal expansions, but every rational number, okay? So you have functions that on an infinite set of points, it doesn't converge. It's equal to infinite, which basically just means it's not defined. But seemingly it does converge to something. How do we deal with this? Well, let's talk about infinity. Okay, let's talk about infinity. Let's figure this out. Let's talk about the way Cantor sort of played around with these ideas, and then how those ideas were used by Radon and Borel, among others, to come up with measure theory. So Cantor, Georg Cantor, he thought that, well, there's different kinds of infinity. Some of them seem smaller and some larger in some sense. Okay, that sounds bizarre, a larger or smaller infinity, but let's figure out what he meant by that. He obviously doesn't mean in the sense of counting, okay, like regular counting. That's not the sense that he meant. But let's put it this way. We have sets like the natural numbers, okay? And these, you know, this 1, 2, 3, so on. We have sets like the rational numbers, which are basically everything like this, where you can write it as a, a ratio of 2 integers, okay? P and Q are elements, that's what that little element symbols, of the natural numbers. We have the real numbers, which include just everything, you know, pi, 4, 1 over the square root of 2, e, tons of stuff, okay? And it might be nice to know, is there any differences in their size in some sense, again we have to say in some sense. Now, we can't obviously count it in the regular way, but what is a feature about counting? What is an important feature about counting? Well, like when children count, what do? Well, when they see like dogs or something, like how many dogs are there in the dog park, or how many trees are there in the front yard, they'll take their fingers out and they'll say, okay, I'm going to pair up each of my fingers with a dog, okay? And I see if I pair those up, my fingers with that number of dogs, and oh, this is 6 fingers, and there's 6 dogs out there. They're the same kind of size. Okay, same thing if it's like, oh, there's only 3, and there's only, oh, that number is 3 right there. Okay, so that's sort of what kids do. They pair up sets like that. They find some way, this finger represents that black dog, this one represents the white dog, this is that brown dog over there. Maybe we can do something like that. We can think of these numbers in some way being paired up. Now again, it's kind of iffy that way because there's all sorts of screwball ways of doing that, but is it possible to pair these different guys up? Well, let's see. The natural numbers. Well, this is the most straightforward kind of infinite, right? This is where we first learn about infinity. You can't imagine any. This is just the beginner's one. This seems bigger in some sense. This seems bigger in some sense. All right, but are they? Let's use this. Let's use this idea of pairing things up. Can you form a list where this is paired up with some element there? This is paired up to some other element. Well, you can. Okay, you can. You can actually pair these guys up. The way you can do that is by saying that, let's just take a table like this, okay? Nice, big table. Alright, let's put 1, 2, 3, 4 up here, 1, 2, 3, 4 here. And this basically represents numerators, and this is denominators, okay? So this is going to be 1 over 1, let's see, this is numerator, so this is 2 over 1, this is 3 over 1, this is 4 over 1, this is 1 over 2, 2 over 2, 3 over 2, etc. Okay? We keep doing it like this. And we keep coming up with more numbers in this fashion. Alright? Now, I can use this to pair up with the natural numbers, okay? I can say, oh, this is the first one, and the second, third, fourth, fifth, sixth, seventh, 8, 9, 10, 11, 12, 13, 14, 15. So now I have a nice little list, just like a child does with his fingers, comparing it to the numbers of trees in the front yard, or the number of dogs in the park. I can do, okay, 1, alright, I'm going to put 1, 1 there. Then we'll do 1/2. Then I'll do 2, 1. Then I'll do 1/3. And you see here that this is going to cover every fraction in existence, every rational number, onward and onward. And if you have a problem with the fact that some of these are repetitive here, then that's fine. You can just skip the ones you've already seen before. Okay, so like I get to 2, 2 right here. And it's like, oh, well, I've already seen that one before. Let's just skip straight to 3, 1. Okay? So I basically matched up perfectly all of the natural numbers to all the rational numbers. And in this weird sense of, can you sort of count one off to the other? Can you pair them all? One to the other. In that sense, these two guys are the same. What about the natural numbers to the real numbers? Can you do that? Can you do, again, a list like this where you say, okay, 1's going to be pi, 2's going to be 4, 3's going to be 1 over the square root of 2, so on, and so on. Can you do that? Can you actually pair these guys up? Well, no. No, you can't actually, okay? And I'll show it this way, alright? Let's first realize that the real numbers is the same cardinality as 0, 1, the interval 0, 1, okay? You can see that by, here's the interval 0, 1. I can pair that very easily with, let's see, how do I represent this? So I'm going to make sure I'm clear. This is with this circle, sort of. Yes, like that. Sorry guys, just having a slight bit of, okay, yes, like this, okay? So I can pair it up at least with all the positive real numbers this way, okay? I take all the real numbers, okay, and I put them up, I move them up to this quarter circle right here, okay? I can do this very easily. I can just shift it up. And then I can just take a line through here, and I can then pair up everything on this circle with somewhere on the real numbers, okay? So this way I've got 0, I guess excluding 1, can be matched up completely with the real numbers, like that, okay? And if you want to do it the other way, then it's just like, okay, just put that circle like this, and then draw the lines out like that, okay? So, in this sense, the real numbers have the same cardinality, same size, in that very broad way, as this interval. Okay, that's great. That's great. So, alright, let's try to handle this. Are these guys right here the same cardinality? Well, let's just deal with the simpler case of 0 to 1 and the natural numbers. Are those the same cardinality? I'll add up the endpoint because, it's just 1 point, it's not a big deal. Equivalent to natural numbers. Well, let's say we did. Let's suppose we could. And by the way, I'm just going to represent the real numbers using binary for a reason which I will specify in a minute, okay? So I have a list. 1, 2, 3, 4, 5, so on. And on each of these members of the list, I'm going to have a real number here, like pi, or 1 over pi, 1 over the square root of 2, and 2 divided by e, and so on, okay? And these will look like this. I'm going to represent these numbers with a binary representation, which feels kind of screwy while I'm doing that, but you'll see why. Like this. Okay, so I have this list. I'm supposing I have this list. Now, okay, can I make an element that this list doesn't have? Is that possible? Yes, yes it is. You see this right here, this 0? What if I took a number and I made this its first place 1? And I took this second number here, I said, oh, that's 0, let me flip that, I'll make that 1. And, oh, look, this third place, that's also 0, so make that 1. And this fourth place, I'm going to flip it and make that, oh, and I'm sorry, oh, here, finally a 0. Like this, okay? So in the first guy, I'm looking at the first decimal place, second guy, second, third guy, third, fourth guy, fourth, okay. Is this element on this list? No. It can't be in the first place, right? Because this guy has a 0, well, this guy has a 1. Can't be in the second, because in this second place, this guy has a 0, and this guy has a 1, and I flipped it. So on and so forth. No matter what, at the end place, I will get to some place, like a 0 or a 1 there, and again, it will be flipped at that end place. Okay? So this element is not in that list. There's no way, so whatever list you make, no matter what pairing you make of all the natural numbers to the real numbers, you cannot pair every one of these natural numbers with every one of the real numbers. Okay? You will always be able to find some real number excluded in this list by this argument, which included this diagonal, known historically as the diagonal argument. Okay? Okay. Alright, so just to conclude that, by sort of generalizing the idea of size, we sort of came up with this idea of cardinality. Can you make a list from one to the other? And why is it a natural idea? Because again, that's what we do when we count, right? That's what we do when we take our fingers out to compare, or we are looking at a lot of sheep, like ancient shepherds do, and we put pebbles in the bag for every sheep we see. Okay? These guys right here, turns out, by this generalized idea of size, known as cardinality, are the same. Well, these guys and these guys over here are the same, the reals and the interval 0 to 1. But these guys are different. Okay, these guys have a different cardinality. And because this is, traditional counting, right? 1, 2, 3, 4. We call this countably infinite. Well, since this is in a sense bigger than that, you can't put it in correlation with the numbers you count. This size of a set is uncountable. Okay. Okay. Why do we care? Why does it matter? Let's see. And again, how does it even matter to all that stuff I talked about earlier? Alright. So, let's, one thing that's really important to talk about in math is the area of things, or their length, right? So, I have some set, something, it's like, okay, this part to this part, this part to this part, these parts, like a whole bunch of, I have some set that's like that, okay, where it's these different sections here. I would like to know what their length is, what their size is, okay? How do I do that? Well, what's a familiar way of measuring length? Well, just that. You just say, okay, what's an interval? that goes from here to here? Well, that could be something like 4, 5, and this is 7, 8, and this is like 9.5 to 9.6 right here, so on, okay? And basically I take the length of all of these guys, and over here it's kind of a mess, so what I might do is I'll just take, let's see, 1 second. I'm not exactly sure how to measure that because it's such a mess right there. So I'll just maybe take some broad estimation like that, okay? And after taking all these different lengths right here, from here, which here it's 1, here it's 1, here it's 0.1, here's maybe 0.1. To point, 2 right here, I find out, okay, the length of this set right here, I'm going to call the set A, is going to be less than the sum of all these guys, of like 1 plus 1 plus 0.2, 0.1 plus 0.2. Okay? Alright, so that's fine to hear, but, and, is this relevant? Is this relevant? Yes, this is relevant. Okay, so we have this idea of like, okay, we can sort of approximate the value of this length by taking this set of intervals, okay? And if I want to get a better estimate, I might say, okay, this is one way of doing it. I could do it again with these same guys, but maybe I'll split this up into a whole bunch of smaller ones, which again will cover things that are not in the set, right? That'll include things which are not included inside of A, but again, it'll be pretty close. And maybe the second time I do it, it'll look like plus 8.01 plus 0.02 plus 0.15. I'll be refined this estimate here, okay? And the idea is that what is the length of this set right here? What is its area, so to speak? Well, that will be what basically these approximations will tend towards, okay? As in, you can imagine that, okay, for the first one I was getting like 2.3, excuse me, 2.3. The next guy was like 2.1, let's see, this is 3, that's 4, 5. And the next guy might be something much more complicated, depending on how I do it. And basically, I keep refining these estimates, and eventually it's tending towards some value. And basically, whatever basically these better and better approximations tend towards is the length of that area. Okay. This is a very similar idea to what's the area inside of this disk right here. What's the area inside of this disk? Well, I'll take a square to approximate the first time, and I say, okay, area of this disk, I'll call it the disk D, it's less than 1. I know it's less than or equal to 1. And then I take a better approximation. That's, boxy like this. So on and so forth like this. Made up of a bunch of little squares because, I understand squares. And so on. A whole bunch of squares inside of here. And I find, okay, the next approximation is maybe less than 0.73. And the next approximation is like 0.7121, and the next approximation, so on and so forth, guys, right? Right? It just keeps going on and on and on. We say, whatever these better and better approximations, as I keep refining this down, will be the area of this guy, okay? Starts off with a very rough one, this big square, goes to a much better one, with these smaller squares to an even better one with far, far smaller squares that keeps in far less irrelevant stuff. And I say, okay, that's what it's tending towards. Alright? Okay. So, that seems like a good idea for defining length that way, of basically what is basically the lowest, what is the lower bound on my approximations of the area using intervals or squares. Alright, well let's deal with another situation. Okay, let's say we had some points. Okay, what's the area of a point? Actually, let's just start off with that. What's the area of a point? Well, by this set. So this point is P. What is the length of that point? Well, I want to say 0, right? Because that's usually how we think about points. It's area length 0. But is it? Is it by this definition? Well, let's see. I can cover it with this interval. Let's say it's the 0 point. I can cover it with negative 0.1 to 0.1. So I know it's less than or equal to 0.2, because that's the length of that interval. I can cover it with negative 0.01 to 0.01, which would be 0.02. I can cover it with even smaller ones than that. Do I get like 0.0002? I can keep doing this on and on. And basically you find, oh, because I can cover it with arbitrarily small intervals, this is less than every single positive number. X is positive, and this can't be negative, obviously. So if you're smaller than every positive number, and you're not negative, that means you equal 0. That's supposed to be L, by the way, if you're not clear. Okay. Okay. So we found that the area of a dot is 0. That doesn't seem very exciting, but okay, at least it lined up with our intuitions here. What else should we do? Well, another interesting situation is what if I had an infinite number of these points. Alright, let's say I had all the natural numbers. Every goddamn one of them. From, like, I'll include 0. No, I'll exclude 0. 0 doesn't deserve my time. I still wrote it though. 3, 4, 5, so on. Alright, how much area did this guy have? Well, way I can figure out this is I can take intervals that are getting smaller and smaller. Like that, okay? This interval has a length of 1. Actually, 1/2. This one has a length of 1/4. This one has a length of 1/8. So on and so forth. And I find, oh, the area of the natural numbers, the length of the natural numbers, is less than or equal to the sum of 1/2 plus 1/4 plus 1/8, so on. Oh, I know what that equals. I know what that equals because I know this square. This is a 1 by 1 square. This has an area of 1/2, 1/4, 1/8, 1/16, so on and so forth. This sum right here, that equals 1. That equals 1. Alright. And, but things, I can tighten this up, right? I could, instead of making this 1/2, I could have made this 1/4, or 1/8, and 1 whatever. That's an 1/8. And 1/16. I could make this less than or equal to 1/2 if I wanted to, or less than or equal to 1/4, or as little as I wanted to, really, where x is positive, smaller than any positive number. So that means that this guy right here, the length of the natural numbers of this infinite set of points is equal to 0. Is equal to 0. Okay. Okay, that's impressive, kind of, but again, whatever. Let's go wild. Let's go with the rational numbers now, okay? What are the rational numbers like? Q. So the rational numbers, I've just drawn them, right? I've drawn all of the rational numbers. Here. Because they're everywhere. They're there, and they're there, and they're there. They're anywhere you look, you will find rational numbers because they're dense through here, to the technical term. What is their area, right? What is the area of the rational numbers? Now, let's make this a little more straightforward. Let's say the rational numbers on the interval 0 to 1. You want to say 1, right? Because they're everywhere. They're every goddamn where. So, what do you do? But are they? Do they really fill up the entire line? Because, you know, there also are the irrationals. And what are those guys doing? Let's see, I guess I'll write this as R take away Q for the irrationals. There's also those guys, and those are also everywhere. Doesn't that equal 1? This is screwball, right? Because this is everywhere and this is everywhere. How can they both equal 1? So, alright. Let's apply this. How is this relevant here? What do I know about this that I know about that? Well, for one thing I know, this is a countable set. Like Cantor taught us. This set right here, the irrational numbers, that is uncountable. I didn't demonstrate that earlier, but you know, it's everything else in the real numbers besides that. It's the uncountables. What happens here? Well, this right here, since this is countable, I can make a list, right? Here's 1, and here's like a whole bunch. Here's a list of natural numbers, and here's a whole list of different rational numbers like this. 2/3, so on. Okay? What can I do with that? How is that useful? I can wrap, just like I wrapped all of these natural numbers with these smaller and smaller intervals, I can wrap all the natural numbers with smaller and smaller intervals. I can wrap the rational numbers that way. I can put around 1/2, the interval 1/2, and I put around 1/8, the interval for 1/8, and I put around 0.015, another one, and another one, and another one even thinner than that. And I find, oh, this is small, less than or equal to the area of 1. But of course, I don't have to stop there. I could have made it like this, where it starts at 1/4. Or I could have made it even smaller, where it starts at 1/256, or whatever. I could make that arbitrarily small. And I find that the rational numbers are less than every single positive number, which means that they equal 0. They equal 0. So, where do we go from here? They equal 0. Well, one thing about that we find is that, oh, if the area of the, let's rewrite this. If the area of, 0 to 1, that's an interval of 1, right? That is area 1, obviously. Well, what is 0, 1, and you take away all of the rational numbers, right? You take their complement, which is all the irrational numbers, right? Well, that equals the length of 0, 1 minus the length of all of the rational numbers, well, inside of 0, 1. And that right there is 0. Right? That right there is 0, and that right there is 1. So this equals 1. So, all of the irrational numbers from 0 to 1, that's basically the substance of it. Almost all numbers are irrational, at least if you go by length. And the real payoff for this comes in the fact, in that earlier situation I talked about, of, oh man, I'm adding up all of these different signs, some of them pretty normal like this, some of them really thin but with lots of spikes. I added these guys up and it feels like, oh, well, you know, their areas are getting smaller and smaller, so when I add these up, like that'll equal a real genuine function, because this later stuff adds almost no area to it. But I have the situation where when I add these guys up, they equal a function such that if I put anything like this into it, where it's like a finite decimal expansion, this thing equals infinity. And I'm thinking, but at every of the rational number, every other number besides that, like pi, or even just 1/3, to make life kind of simple for me. At these numbers, it does actually equal a number. Okay, I can show that. So these guys equal real finite things, while on these finite expansions, they equal screwball stuff, right? Now, right here, what's important about that? About the fact that it's only these guys that it goes that messes up. Well, these guys are basically all this are a subset. The finite decimal expansions, those are all inside of the rational numbers, right? Right? That's a smaller set because these guys can all be written like as in, and take any finite decimal expansion like this. This is equal to 1215 over 1000. 10,000. Okay? So this is the rational number, right? So it belongs inside the rational numbers. I know that this right here makes up 0 area. Okay? It doesn't matter. It's such a small amount of it that as far as the area is concerned, as far as the measure is concerned, it's nothing. So, and I find, oh, and every other point, what actually works, that's basically everything. That is basically everything. If you have 0, 1, what is the length or the measure of, what is it called, 0, 1? Take away the finite decimal expansions. What is the length of that guy? That is just equal to the length of the regular interval. Because this doesn't count. This is nothing. And what's really important here, the reason why we care about this distinction between uncountable and countable is if you're doing something where I'm adding up a whole bunch of these different functions and I have serious problems on a subset of the points, the subset of the domain of the function that I'm approximating, if it goes to hell on a certain set of points, if that set of points is so small that it has measure 0, I can just say, screw it, I'm going forward with it. That's just almost nothing. Almost everywhere else it works, and through technical mathematical means in real analysis, I can move forward with it, ignoring those bad points, understanding the function as essentially this part and not that part. Okay? That's the cash value of real numbers. That's the cash value of the cardinals, of cardinality, and that is why Georg Cantor is a truly great mathematician for whatever other mistakes he made.